Hi there, look at what I've been doing. I've been doing some compositions here. Not music, no. Composition of functions. Come over here. You remember what a composite function is? One that comprises two different functions, one operating on the other. Have a look around the screen here. Have a look at this one. Sec squared, or the secant squared on x, is secant is 1 on cosine, and then we're squaring it. So a couple of things happening here. And wow, look at that graph. Hey, do you remember that one? What am I doing here? Hey, do you remember that that's what we found when we asked the calculator to find the graph of the derivative of tan x? It actually is sec squared, or 1 on cos squared. We're going to look at why that's so later on. But what we're doing here is saying, can we find the derivative of composite functions? We're going to develop a rule called the chain rule for this. You're going to produce a chain of derivatives. That's interesting. But what about this function over here? That consists of a simple linear function, but look at this one. E, not to the x, but to the linear function in x, which is 2x. Down here, the cube of a quadratic. I wonder if you can expand that and use the x to the n rule. You could, but that'd be a lot of work. I'd rather try to find the derivative or differentiate this as it stands without having to expand it. Interesting graph though. Looks like the x cubed is being distorted a little bit here. There's a few pieces around. And what about this one here? The log of x is okay, but we're not finding the log of x in this function. There's another function living there. We're applying the log function to the square of x. So what we want to do is to find the slope of the tangent, or the derivative, for any of these functions. Okay, so that's very, very important. Just remember the overall trichotomy here. Not a very good circle, that one, mate. But here we are. When we're finding the derivative, what are we doing? Why is it so useful? You've seen so many uses of it now. It's the slope of the tangent, and it is also the instantaneous rate of change of the function. Okay, so they are the ideas that we're playing with. We want to be able to do it for any function. And we've got a couple of other things still to do even after this presentation, but this is probably a key rule, isn't it? To be able to do differentiation or find the derivative of a composite function. Okay, let's go down and see if we can develop something for this and have a look. Alright, first of all, this is supposed to be revision. Okay, so listening carefully about composite functions or composition of functions. This is a composite function. Why? Well, it comprises f of x, the cube of x, and g of x, which is this quadratic, x squared plus 3x take 5. And if I apply f here, instead of to x but to g, what does that mean? Well, in the variable hole there, x, I have to put g, according to this notation down here. So instead of x cubed, I'm going to have all of this cubed. That's the idea, isn't it? Okay, f of g of x. F done on g of x instead of just x. Or it's f, here it is, operated on g. G done first and then f operates on it. Okay, so that's the idea. So what about that now? Could we say something here about this fog? Well, yeah, I hope you're not too foggy about fog. A lot of people are. Just remember, you do the f function operated on g there. So just thinking about that from before. Alright, so hopefully that's clear, and that's our first composite function that we want to look at now. So come down and let's see if we can do something with it. Okay, so coming down now. There we have it. Okay, and this is the way we usually explain it. If y, overall function, consists of a function done on u, and u is itself a function in x, then this is our derivative. Let's look at that for a start though. What we're talking about is if f is the cube of u, and u is this quadratic. It's another way of setting up that composition of functions idea, using a u notation. And what's it say? The overall rate of change of the function with respect to x is the rate of change of the function with respect to u times, that's a derivative with respect to u, times the derivative of u with respect to x. Wow. In other words, we're breaking it into a product of two derivatives. That's where you get, like, this is like a little chain, isn't it? A chain of derivatives. So that's where that name comes from. Okay. Yeah, chain rule. Well, let's see it down here. dy by dx. Let's do the u part first. So the f is the cube of this, call it u here, so it's 3u squared, ignoring this for the minute, just finding the rate of change of this function with respect to that u, and then we'll multiply by the derivative of u, this thing here, which is 2x plus 3. Now that line isn't actually necessary. You could go straight to this one, where you're showing clearly that you're treating this as a variable and just doing the power part. So you're actually differentiating f with respect to this thing as the variable. If you like, dy by this. Okay, you're really just saying, I'm going to ignore the variation in that, and then I'm going to put the variation in that next here, and this is d2x plus 3 by, dx squared plus 3x take 5 with respect to x, breaking it down into two different rates of change. Okay, so that's the rule. We'll see it a bit more clearly in a minute, but although there's no proof required of this rule, I want to respect you as a budding young mathematician. I want you to have a go at trying to understand the chain rule and why we can do this. So I've got a little bit of derivation down here for you to look at, so you might get your head around this a little bit better. So let's have a look now. What are we going to do? Well, first of all, our derivative is our limit as delta x tends to naught of changing y over changing x. Let's just revise that with this little graph up here, just the usual one, of course, here. So we've got the slope of that chord. We're at x, and we go out to x plus h, that stuff. So this is delta x, change in x, and let's stake here, how did the y change? We call that delta y. And the slope of that chord was delta y on delta x, and we were interested in finding what value that approach as you went to tangency, as we came down to the instantaneous rate of change at that point down there. Okay, so what could we do? Well, we know we've got two functions operating. Come over here. This was y was the cube of u, and then u, so u here was x squared plus 3x take 5. So let's look at how the cube changes with respect to that, and then we'll look at how u, which is this, changes with respect to x. That's the idea. Why does it work? Come over here. Delta y on delta x, forget the limit for the minute. That's a change in y over change in x. You could look at how y changes with u from that top graph, and then multiply it by how u changes with x, because that cancels. And that's what you're talking about. You're talking about these little increments here. Delta u, delta y, delta u, delta x. Okay, so they will cancel out. So this is a very important line to understand, that the overall rate of change of the function right back with respect to x, acknowledging that there's another function hidden in there, is the product of these two fractions. Now if we take the limit, it's the limit as delta x tends to naught of this. So this is the crucial breakdown of the two rates of change according to these graphs over here. Okay. So that's showing you visually on the graph of what's going on with those fractions. Now, if delta x tends to naught, because u, let's go over here, u is some function in x. If delta x is going to tend to naught, then the overall function here will tend to naught. delta u. The small change in u would be resulting from a small change in x. So let's get back over here. So we're going to say delta u tends to naught. So the limit is the limit as delta u tends to naught of that bit and delta x tends to naught of that bit. Because as delta x tends to naught, delta u tends to naught. Oh, and what do you notice? Yes, that's the definition dy by du, and this is the definition of du by dx, leading us to a chain of derivatives. So this is called the chain rule. Alright, so there's the proof for it if you're interested in the maths. This is not required in the course, the proof, but you must be able to use the result of the chain rule. Okay, let's go down and try and consolidate that so you don't spin out there. Okay, so here we're going to try and do some exercises. So the way it's usually put is y is a function in u and u is a function in x. So you break it down. The overall rate of change of y with respect to x is a product of the two rates of change, if you like. Or, this is from Pearson's now, if you have dy by dx and y is a composite function, f done on g, what do? You find the derivative of f, leave g untouched, and then multiply by the derivative of g. So you're actually in this first derivative differentiating f as if that g of x is the variable. You're not looking at its variation in there. Now, although this is called the chain rule, I actually prefer people to think of it as the function of a function rule, because it helps the student determine when to use it. The chain rule tells you what you should get at the end, a chain of derivatives. It doesn't help you necessarily get started here. Function or function. Let's use this approach to detect when to use this rule. So I come over here, let's come over here and say dy by dx. How am I going to do this? Derivative of 2x is 2. Plus, oh, what's this? It's a function e of a function 2x. There are two functions in here. Oh, I know. I've got to use the chain rule. Okay, because a function of a function tells me what sort of setup I will need to attack with the chain rule. So let's do this first function. Derivative of e is itself. Remember, you don't touch the other bit. You're actually differentiating e to with respect to 2x, and then you multiply by the derivative of that top bit, which is 2, and there's your chain of derivatives. But I think to work out what you're going to do, it's helpful to identify this as a composite function for a start. Function of function. All right. And generally we won't simplify that. If they ask you to find the derivative, quite often they say do not simplify your answer. The idea being that we can see what you're doing better that way. Let's come to this one now. There's y. It's the log of something which itself is a function in x. I've got a function done to a function. I'm going to use the chain rule. Derivative of ln is 1 over whatever it is. You don't change that. You're differentiating y with respect to this u. Now you multiply by the derivative of that, which is 2x. No need to put in u's in here as such. Okay, so I think really we're thinking about it more along this line here rather than this one up here. Both are the same, but I think choose how you think about it. You must what? Identify the functions. Spot the functions. That's the idea. Spot the functions here is the secret here to working with this rule and looking at finding the rate of change or the derivative of a composite function. Very important rule. All right, let's go down and have a look at this idea here now. This is from Pearson's, so read it in their textbook. The chain rule acquired its name because we use it to take derivatives of composite and we get a chain of derivatives at the end. Okay, but a function could be a composite of more than 2. Oh, if a function were the composite of 3, we would keep that breakdown going, wouldn't we? You remember the graphs? It would keep going. So if we had y as f of u and u was a function of something else, and then v finally was related to x, we'd have 3 different graphs with 3 different ratios all cancelling back to delta y on delta x and finding the limit. So what's an example here? Let's take something like y equals what? Sine squared of 3x squared plus 2x. Can you spot the 3 functions there? Let's do it in the proper theoretical way up here. Let's spot the functions. So, what would f of u be? F of u would be what? U squared, and g of v, g of u, hang on, we'll just do this here. G of v, let's put this in. G of v would be sine of v, and v would be h of x. Let's just put h of x here, which would be 3x squared plus 2x. So if we do g on h, we put that into there, and then we do f on that, we then square it all, and that's what's happened there. Okay, so let's look at the derivative. We do all the pieces. So first of all, it's 2 sine 3x squared plus 2x. Just doing the power function here, the u. Now we must multiply by the derivative of the sine, which is cos 3x squared plus 2x. Derivative of sine is cos, remember. Uh-oh, now I'm in trouble. I've run out of room. Then we've got to multiply by the derivative of h, which is 6x plus 2. Okay. So that's what we've got, a chain of derivatives. This is f dash u, this is u, g dash of v, and then h dash of x. Okay, all of those in a row. Please note, as you do them, don't touch the other variables, don't touch the other parts of the function. Just concentrate on what you're doing there. So when we're doing this power to the 1 less power, 2 sine, you don't touch that. And when you're doing the derivative of the sine, which is cos, you don't touch that. And then you finally get the derivative of that at the end. So there they are there, the 3 derivatives. dy by du, don't touch u. Then you do u, don't touch v. Then finally you do v in all those parts there. Okay, so we've got to identify, spot the functions, so the important part here. So that's why I like to call it the function of function rule. Sure, it gives you a chain. Here's the chain of derivatives, each one multiplied by the other, but spotting the functions is important. So we don't need this, by the way. That's not necessary in this course, so you don't have to identify all that, but you have to in your head. So you have to say, well, I'm going to do the square, then the sine, and then this one. And don't touch the other parts as you're doing a particular function within that composition. All right, let's come down and see what you think about some examples here from Pearson's. Differentiate each function by applying the chain rule. Start by decomposing, starting with the outside function and then the inside function. Okay, so let's have a look at cos 2x. Here they're saying the outside function is cos, and they've said u, cos of 2x. Don't need to bring in u. Bring in the derivative of cos. Derivative of cos, remember, is minus sine. So I'd have minus sine. I'd leave the 2x in there. Don't worry about going to u land. And then you have to multiply by the derivative of that 2x, which is 2. Then putting it out the front, we've got that. Okay. So, and they've got the other notation there. I think this is easier to apply rather than putting in u's, as I've just said. So the derivative of cos is minus sine. Leave this untouched. And then multiply by the derivative of that. So I think that second way is best. Let's look at the next one, the root of 3x squared plus 5x. And so on down there. So what is this? This is best thought of as 3x squared plus 5x to the half, I think. You can read that first one, but here it is here. I think this is the preferred way of doing it. So it's a half, 3x squared plus 5x to the negative half. I'm just doing that fractional power, the x to the n rule, if you like. I'm differentiating that, holding this constant as the variable, and then multiplying by the derivative of that. Do you get it? And then, of course, you can simplify it. Not particularly interested in simplification here, because quite often when you're asked to differentiate something more complicated, they like you to put it like this without simplification so they can spot what you've done. Let's have a look, but you will be needing to simplify it if you're going on to find the equation of a tangent or something like that. So let's look at the next one, ln 1 take 3x. So what will you do? Do the ln part, 1 over 1 take 3x. The derivative of 1 take 3x is negative 3. Derivative of constant 1 is 0. Okay, and then you can simplify it. What about 1 over 3x squared plus x? We would say this is 3x squared plus x to the neg 1, or there it is there. I would avoid using u, you can confuse yourself. So here we are, let's do the neg 1, it's neg that thing to the 1 less power, x to the n rule again, multiplying by the derivative of 3x squared plus x, which is 6x plus 1. Okay, spot the functions. Spot the functions is the important thing here, because it's really the function of a function rule, if you like, and it produces a chain of derivatives. Okay, let's do some more and see if you can get your head around this. Let's look at example 5 again from Pearson's. Find the derivative of the function here by expanding, because that's earlier part of the course, or by the chain rule. So 2x plus 3 all cubed. Oh gee, this is a long way of expanding, isn't it? You might have used a binomial expansion for that. Should really know that, because the coefficients are 1, 3, 3, 1. So it's one lot of 2x cubed and no 3 in there. Then it's 3 lots of 2x squared by 3 to the 1. Then it's 3 lots of 2x to the 1 by 3 squared, and then one lot of 3 cubed. Okay, you should be able to do that either from Pascal's triangle or CNR combination coefficients, binomial coefficients there. Okay, and you would end up with this, and then differentiating it, you'd use repeated x to the n rules here. A long way of doing it now. Okay, so it's 3 by 8, 24x squared, 2 by 36, 72x, derivative of that, and the derivative of this is 0. Okay, let's see what the chain rule offers us for this one now. So here, just taking it as it stands, what are the functions? You've got a cube, so it's going to be, they've left it out here, the derivative will be 3 by 2x plus 3 to the 2 times the derivative of what's in here, which is 2, giving us this one here. Okay, much easier, isn't it, when once you've spotted that it's a function of a function. First function is the cube done on 2x plus 3. Composition of functions. Okay, let's look at the final example and then let you loose and see if you can have a go. Find the derivative for these functions. Sine squared is an abbreviated way of saying sine x all squared. So it's quite useful to put it like that. So it's 2 times sine x to the 1 by derivative of sine is cos. Okay, 2 sine x cos x. And you might recognise that 2 sine x cos x is the sine of 2x, I think, from your formula book if you don't remember it. Let's do sine of x squared. That's a little bit different. It's just the x squared. So the use of a bracket is quite useful. It's not what we did before there. Okay, so what are you going to do? Let's do the derivative of sine there, which is cos. Leave the x squared untouched, and then do the derivative of x squared, which is 2x. Okay, then you would put this 2x in front so you don't confuse finding the cos of all of those x's together. That's got nothing to do with it. It's 2x out the front and cos of x squared only. Okay, what about e to the sine x? That's interesting. Okay, the derivative of e is itself. I'll go straight here. I think you should go straight here. Derivative of e is itself. Leave this untouched. Then deal with it. Derivative of sine is cos. Okay, you can see what Pearson's done there. Pause the presentation and study it if you wish. I would like you to go straight from the function. Here we are. Here's a function using our power rules. Cube root is rational power of a third, so it becomes 2/3. And then let's go down here straight away. You don't need these working lines here. So derivative of that power 2/3, the function to the 1 less power, 2/3 take 1 is -1/3, multiply by the derivative of what's in bracket there, -5. And then you can simplify it. Interesting comment here from Pearson's. Aim to write a function in a way that eliminates any confusion regarding the argument of the function. So sine of x squared rather than, in brackets, rather than sine x squared. 1 plus ln x rather than ln x plus 1. So you don't think somehow that the 1 is involved in the x term. And 5 plus root x rather than root x plus 5. So you don't actually include that under the root sign. Get the idea? Trying to accurately, what are we doing? Spot the functions. Okay, that's the important idea here. And then do the derivative of each one, according to our rule and what we established earlier. Alright, are you ready? Okay, there it comes. Here's an interesting one. Okay, what about the derivative of ordinary exponentials? We know that derivative of e to the x is itself. Gee, that's an important result. Okay, a function whose rate of change is exactly equal to itself. But what about other ones? How can we do those? Let's say we're talking about positive values and b is not 1, so you can have fractions from 0 to 1 or greater than 1, not just b equals 1, because that's just a flat line, isn't it? 1 to any power is 1. So what do you think our goal would be? I reckon we've got to use this. Can we attack any base raised to the x via e? And of course we can. Look, here it is, here it is, here it is. E to the ln x is x. That's our definition, isn't it? That's an algebraic way of writing a definition of ln, because ln is the power you raise the base to get the number x. And we're doing it. We're raising e to the required power. We must, by definition, get x. That is an algebraic statement of our definition of logs. So, let's do it to b. There's b, and we want to work with b to the x. Don't call b to the x. Nah, don't do that. Write it as a power of e. Why? Well, we know how to differentiate e, don't we? So the thinking here is any base, convert it back to a power of e. Okay, so if you're looking for finding the derivative of any power expression, think, power expressions are attacked through the avenue of the exponential function, and I'm going to convert it to a power of e first. Let's have a look at how we do it now. I've got this laid out here for you nicely. Okay, we just come up here just a little bit there. Okay, so first of all, let's operate on b to the x. So b is e to the ln of b from that definition, all raised to the x. Now, a power raised to a power is the product of the two powers. So our b to the x is e to this much here. E to the ln b times x, multiplying the powers together. Now let's find the derivative of it. The derivative of this line here is what? Okay, derivative of e is itself. Don't touch this, remember. And then we multiply by the derivative of this. ln b is a constant. It's a power of x, so the derivative of ln bx is ln b. Now you know why we've had to wait, because we needed the chain rule to be able to attack this function of a function. The two functions there, spot the function. And we needed this rule, function rule, or the chain rule, to be able to identify the parts and deal with it. So what is e to the ln bx? Well, that's just b to the x going backwards again by ln b. So that's our result. Let's have a look at the generalisation. We would do this for any of them. Derivative of b to the x, if b is a positive constant and not equal to 1, then the derivative is itself times ln b. Or in Leibniz notation, doing the d by dx, itself times ln b. I like students to think of ln b as a sort of conversion factor. It's what we need to have in our expression to convert a standard exponential expression b to the x, a to the x or something, to an e form, because e is the exponential function. So that's the idea. Okay, so that's the winner there. And if you've got anything else, you have to have ln b next to it, because from our proof up above there, the derivative is b to the x, not itself, but with our conversion factor there. So I think through that in that way. Alright, so if I gave you y equals 2 to the x, the derivative is itself times conversion factor to bring it to eland, 2x by ln 2, and so on. Alright, think through. It's good if you can get up and close and personal with it and understand that proof above rather than just learning off rules, okay? And this is where I want to tap in to that proof from above, LMB as a conversion factor, thinking, oh, I've got to work on b to the x because it's not e to the x. E to the x is my special one. Okay, no worries. Come on. Are you still with me? Let's have a go now at some problems. And I'm going to, as usual, bring up the problems here, question 1 and 2, right the way through. Pause them as you need to do the problems. Try to do all of them, and then scroll down, because as usual, the fully worked solutions are coming on below. So this is Pearson's chapter 13, section 2. All right, so pause presentation, have a go at some of these. But as you do one or two, toggle forward so that you can check them. Don't do everything and try to mark it all later on. Okay, 1 and 2. I think there are 9 here in this set. Okay, so that's 3 and 4. Bring in other aspects of the derivative, tangents and things like that. And 5, 6, 7, 8, 9. Okay. That's good. Let's go and look at the solutions now. So there's question 1 through almost to K. We'll have a look at that in a minute. Try not to work across, work down the page. Much easier to mark, standard convention. Pearson's have done it here to save space. Alright, let's go and look at some more here. Let's go down, we'll just keep K in there. Question 2 and 3. K and L from question 1. Mark question 2, we'll bring 3 up in a minute. Okay, there's question 3, part of 4. Rather than this table, it's often useful to draw a displacement line, isn't it? And map it out at various points. Okay, let's look at question 4. Alright, get that on there. Okay, see if we can get the rest on there. Down to E. Question F and part 5. Can we get 9 on? Not quite. and there's 9 there. Right, you should be feeling pretty happy. It's stepping up, isn't it? And hang on in there and just go back over the presentations there and consolidate. But you should be very proud of coming so far. We haven't got much further to go with derivatives of functions. We're nearly there. The next presentation will knock that over, and then we'll look at some good applications. But for now, it's cheers from me. Catch you later on.